So here we're going to test do a hypothesis test again, but it's going to be the difference between two sample means from two independent samples. So really what that means is that the samples are not necessarily like coming from the same population. They're like two separate groups, and one is not going to really have an effect on the other one. Okay, so there's just a few things that change a little bit here. So let's just begin with a situation that why we want to know about the difference between two means. So scores on a National Assessment of Education Progress Progress Mathematics test range from 0 to 500. In a recent year, the sample mean of students using a computer was 309 with a sample standard deviation of 29. For students not using a calculator, their sample mean was a little lower. It was 303 with a standard deviation of 32. So it's lower and they're a little more spread out. Assuming there were 60 students in the computer sample and 40 in the sample that did not use a computer, we can see that the sample mean scores differ by 6 points. What we're really interested in is the difference is this difference between these two means, is it significant? So it is plausible the difference between the population's means could really be 0 if we looked at the population opposed to two samples. We expect two samples to not look the same, and these ones are not very far from each other. So this simply could just be random chance. And that really, if I looked at the population of those who are using computers and the population of those not using the computers would look the same, that actually they would have the same population mean. That is possible. We want to see if there's strong enough evidence that the population mean of the scores would actually be different. So we don't have the population data, we just have some samples and we're trying to guess what would happen with the population. So this is an example of a situation in which the data consists of two independent samples. They didn't come from the same group. We got one that's just people who used computers and one was a group of people who didn't use computers. So two samples are independent if the observations in one sample do not influence the observations in the other. They didn't. These are two separate groups. Two basically, like they're operating in two different ways. They did not overlap in any way that we're aware of. So they should be really considered two independent samples. What happened to one should not impact what happened to the other. So here, our null and alternate hypothesis are a little different. So the issue is whether the mean scores of both population of students, those using computers and those without, are equal. In other words, so we're going to have sample one is going to have a mean that we're going to call mu1, and then we would have sample two that's going to have a mean that we're going to call mu2. Not the Pokemon though. So what we want to know, not really necessarily about the sample, but about the population, right? So we have sample data for us, but what we want to see is the population means, would they be the same? So the null hypothesis would basically be, yeah, they should be exactly the same. The alternate hypothesis is either one is smaller than the other, or they're different. We don't know how. So it could be that the population of one has a mean that's smaller than the population two, or it could be population one has a mean that's greater than population two, or all we can say is population one and two are just not the same. So it's all depending on what is the claim that we're trying to look at. So we use the following notations. Mu1 and mu2 are population means, x bar 1, x bar 2 are sample means, S1 and S2 are sample standard deviation means, and N1 and N2 are sample sizes. So clearly all the ones belong to the same group and all the twos belong to the same group. So the test statistic is based on a difference between the two sample means. So that x bar 1 and then x bar 2. So the mean of x bar 1 minus x bar 2 is just going to be mu1 minus mu2. We approximate the standard deviation for our standard error is going to look like this. So the standard deviation of sample 1 over its sample size, let's try this again. It is the square root of the variance of sample 1 over sample 2, or over sample size, plus the variance of sample 2 over its sample size, add them together, and we do a square root, and this gives me my standard error. So this is basically the standard deviation. The test statistic, if we want to have our t, is going to be x bar minus x1 minus mu1 minus mu2, and then we're going to divide by that standard error. So the degrees of freedom is going to be equal to whatever is smaller between n1 minus 1 and n2 minus 1. So there's quite a bit of work and calculations for this. So we're going to do it at least once with the calculations, and then we'll see how we can do this with a calculator and move this along a little faster. So we're still using the same assumptions that we've been using before, with just a little extra added. So we're assuming that we have simple random samples. So they're just simply random. There's nothing else we have to worry about, any kinds of sampling techniques. We still see that our sample sizes need to be large, or our population needs to be approximately normal to make sure that our distribution of X bars is normal. The only thing that's really added is this part right here, which says that the samples are independent of one another. So we make sure they're independent samples. So these are all the assumptions that are being made here while we're doing these calculations. Okay, so we're going to do the p-value method first. So we still need to state a null and alternative hypothesis. We need to make a decision, choose a significance level. Then we have to compute a test statistic, and then we'd have to do a p-value and decide it's left tail, right tail, or two tail. So nothing's really changed here. Interpret that p-value and decide if we reject the null hypothesis and state our conclusion. So pretty much most of this is exactly what we've been seeing all along. And once again, if my p-value, if we're doing a left tail test, this is going to happen if we're saying that sample 1 or population 1 is smaller than population 2. Right tail test is if we say that the mean of population 1 is larger than the mean of population 2. And the two tail is when we say those population means cannot be equal. Okay. So really the only big difference here is just a little bit about the setup and how we calculate our test statistic and our standard error in our means. So it's just a little change in some of the calculations. So that same problem again, National Assessment of Education Progress Test. We found that in mathematics that those who used a computer had, so this is going to be sample 1, computer. What we see is that they had a sample mean, so X bar 1 is 309, and they had a standard deviation, so S1 of 29. We were also told later that we assume that 60 students used the computer, so N1 is 60. The other sample we have is sample 2, which is the ones that use no computer to take their test. And we see from here that for students who use or did not use a computer, so they're going to be my sample 2, so they're going to be a mean X bar 2. For them, their mean was 303. Their standard deviation, so S subscript 2, was 32. And then we're told down here that for 40 students in the sample, we had 40 students in the sample that didn't use a computer. So N2 is going to be 40. Okay. So what we need to do is we just need to set up our test. Okay. Second. So what we need is when we do this a p-value test. We need to decide what kind of p-value test that we are doing. So we have here, can we conclude that the population mean scores are different? So what we're looking for is that we want to show that there's a difference between the two scores. So my null hypothesis is that the scores do not change, what's always the same. But we need to show that the mean scores are different. And what we see here is that sample one is, oh, sorry, it's just different, not one's bigger than the other. They just need to be different. So we just need to say that mu1 is not equal to mu2. Sorry, I thought I was doing a one-tailed test for a second. So this is a two-tailed test. So we said alpha is 5%. So that means we have half of alpha is here, and we have half of alpha is here. So we need the t-scores for those critical, for these, actually I just tried to do a critical tail test. Let me go back and fix that for a second. But this is, yeah, what we're looking for is this two-tail test like this. Sorry, I was trying to do a critical value, but we're doing p-scores instead. Okay, so what we need is we need to find our test statistic. So T is just x1 bar minus x2 bar, and then minus mu1 minus mu2, and then that is going to be divided by the square root of the variance, so s squared of 1 over n1, and this is going to be plus variance of sample 2, so s squared of sample 2, and then we have n over 2. Okay, so first part of this is easy. If mu1 minus mu2, if they are the same as my null hypothesis suggests, that means that this difference would have to be equal to 0. So really this difference kind of gets negated and we sort of ignore it. And we said that x bar 1 is going to be 309. X2 was going to be our 303. And like I said, basically this disappears, so we could say subtract 0, but it's not really going to add anything. But if we do the standard error down here, S1 was 29, so that's 29 squared divided by the sample size of 60. And that is plus 32 squared, because 32 was my standard deviation of the second sample, and then our sample size was 40. So if you stuck this all in a calculator, second, I gotta move something on my screen, we're going to get T is 0.953. Okay, so what we need to do is we need to figure out my p-value. So since that we're looking at a larger test statistic, so remember we're thinking this is being centered at like 0, we're going to be looking at 0.953 is going to be here. So what we're going to look for is the area in this tail. So I need the p for a t-value being greater than 0.953. All right, so we need that. So to do that, we need our degrees of freedom. So degrees of freedom, we have a sample size of 60 and a sample size of 40. So my degrees of freedom are either going to be 59 or 39. And what we end up picking is, if you remember, we said we picked the smallest of the two. So we're actually going to pick that 39. So we need to go figure out the probability of this event. All right, so once again, if I want to figure out that probability, I go second bars. I go to number 6, so TCDF. So we're binding by t-scores, right? So we're bounding between 0, 953, and infinity. So we make sure we put that in here. Our degrees of freedom, like we said, we took the smallest degree of freedom we have between the two samples. So it's the smallest sample in its degrees of freedom, which is 39. And then we go down and we hit enter. So we get this area, but remember it's a two-tailed test. So it's actually going to be double this area. So this is 0.17323. We'll round it to there. I just want to double that. So the quick way of doing that is just go 2 times second, and then we see answer right above here. And I'm going to get 0.346. Okay, so we said alpha is 5%. So we see that P is greater than alpha. So let me put my hypothesis test here again. What we had as that null hypothesis was that the population means we expected them to be the same. The alternative hypothesis is we just expected that they would be different. And we have a situation where we are going to, because P is greater than alpha, we fail to reject the null hypothesis. So we don't have evidence that the population means are different. And really what it is we do not have evidence that those with computers and without test differently. So there's not a big enough difference between the means. We do not have evidence that the population means are different. We'll just say very different because we expect them to be maybe a little bit, but we are generally expecting not to be very different. And the mean scores may be the same. So what we have here is we don't have evidence that people with computers and without are necessarily testing differently. Like basically that having a computer and using that for a test is not giving you advantage over those without a computer is really what we're seeing here. Is it does not seem to be that having a testing with the computer or without is going to make a difference about that exam score. So there is an easier way to go about doing this. So remember, when we go to stats, we have these tests. So we have 2 sample t-test. So because we're looking at comparing 2 samples, we are going to do the 2 sample t-test. So we don't have data that's entered, we have stats. So we're going to go to stats. And what it asks you for is that first initial information. So your first sample, we had a mean of 309. The standard deviation was 29, and my sample size was 60. So my second sample had a mean. So my x2 is, or x bar 2 is going to be 303. My mean of the second, or standard deviation of the second sample is 32, and the size is 40. And our test was saying that the 2 populations are not equal. And we're not pooling anything. So leave everything alone. So we just make sure to say that these are not equal, and then we hit enter. So I'll show you that we did the correct test here, and we'll see we're getting that same information. So there was a little rounding error on our part because we rounded, there was some rounding somewhere, so our numbers are not exact here. Our t is, though. We still got the same t, and we see that the p-value it gives us is 0.343. We had 346, so it was just slightly different. But still, p is greater than alpha because alpha was 5%. We fail to reject. We fail to reject the null hypothesis. We don't have evidence that the two populations are really different from each other. Okay, so having that ability to just do the the two sample test in our calculator is going to make this one a lot easier to do. So we have one way to measure a person's fitness is to measure their body fat. The average body fat percentages vary by age, but according to some guidelines, the normal range for men is 15 to 20% body fat, and the normal range for women is 20 to 25. It is believed that women who do workouts at the gym will have a higher percentage of body fat when compared to men who work out at the gym. So we're looking at two populations here. So we're going to look at men. Men is going to be population 1. So we're going to be looking at comparing the mean of men to the mean of women. We're going to call them population 2. So we have this null hypothesis is that they would have the same size or same body fat index. Our claim, however, is that we expect that men are going to have a lower body fat content than women, and these are out of ones that work out, so not just the average population. So it is believed that women who do workouts will have a higher percentage of body fat than men. So the mean for women should be higher than the mean for men. So our sample data is from a group of men and women who do workouts at a gym 3 times a week for a year. Then their trainer measured their body fat. The table below shows the data. So this is the percentage of body fat that they had. So we had a few more men than we had women. All right, so we could go through and calculate the mean, the standard deviation, and all that. There's an easier way that we can do this. So we have this whole table of information. And just to point out, this part here is my claim. So I'm going to see if I can support that claim. So let's go up to the TI 84. So as you see, I entered in all that information. So I have L1 as my men and L2 as my women. So I go to stats. I'm going to go to test. I'm going to go to number 4, 2 sample t-test. So here I'm not going to do stats. I'm going to do data. And I'm going to say list 1. So list 1 is my men. So I'm going to put in L1, L2. List 2 is my females. That's L2. Don't mess with the frequencies. And we are saying that we expect L2 is greater than L1. So we see that lines up, it says mean of 1 is less than mean of 2. So this would do us for us. So our test statistic, if we wanted to figure that out, our test statistic would have been a negative 2.6. Our p-value is going to be 0.008. So what kind of test would we were doing? Well, we're doing a test like this because we're saying that the first population is smaller than the other one. So this was a left tail test. So we set it up the way we did. And we're saying that basically this area has a 0.008% probability here. We also see it gives me my mean for both populations, my standard deviation for both populations. So it will calculate all that data for me. It even tells me what my sample sizes are. But let's say alpha is 5%. I believe that's what I said. Let me go back and check very quickly. Oops. Oh, I didn't specify. Okay, I didn't specify, so it's 5%. So we have that P is less than alpha. So we reject the null hypothesis. So we have evidence that women are actually do have a higher body fat than men. So we have evidence that women who work out still have a higher body fat count than men who work out. We supported the claim. Like I said, alternately, we could have went through and you could have just looked for found your mean, your standard deviation, your S. We could have went back and calculated your t-score, and then we could have compared it to, and then we could have went back and calculated that probability. But if we use this test here, then it'll do all that work for us.